Okay, this video is going to be looking at the 2014 Edexcel June 2014 FP1 paper, and it's going to be looking at question 3a. And the question says, given that 2 and 1 minus 5i are roots of the equation x cubed plus px squared plus 30x plus q equals 0, then write down the third root of the equation. Now, this is a nice easy 1 mark if you know what you're doing. So I presume that you're here watching this video if you're kind of a little bit unsure of why the answer should be what it is, because it is a really simple answer. Okay, so I'm going to hopefully take you through a little bit of why the answer is what it is. Now, in general, if we have a cubic equation, which is what this thing is here, it's a cubic equation because the highest power is 3, so we call it a cubic equation. Okay, so I've just written down a general cubic equation here where a, b, c and d are just ordinary numbers, just like you would have with a quadratic. A, b, c and d are just ordinary numbers. Okay, now a root will occur when y equals 0, because remember, a root will occur where a graph crosses the x-axis. Okay, that is the x-axis is the line y equals 0, so we call that where it crosses the x-axis a root. Okay, and a root will occur when y equals 0, so when this whole thing equals 0, because of course y is equal to all of this thing, so if you set all this thing equals 0, that's the same thing as saying y equals 0. Okay, and there's 3 different scenarios. Okay, remember that the number of roots of any polynomial is always given by the highest power or the highest degree in your equation. Okay, so in this case it's a cubic, so the highest power is 3, so therefore there are going to be 3 roots. So there's going to be 3 places potentially where it's going to cross the x-axis. Okay, so let's look at the first situation. So 3 real roots. Okay, and let's call these roots. It means that basically you can factorize this thing, this cubic, like this. Just like you'd factorize a quadratic into 2 roots, you factorize a cubic into 3 roots. So this thing multiplied by this thing multiplied by this thing all equals 0. Okay, and then that implies that the roots are going to occur when x equals alpha, or when x equals beta, and when x equals gamma. Okay, and I've drawn a little pretty diagram to show exactly where the roots are. So there's going to be one root over here, another root here, another root here. And equally, if it was a negative quadratic, so that if the leading, if a was going to be negative, then it would just be this thing, but the other way up. So there's going to be one root here, and another root here. Now this is just a very rough drawing, just to give you an idea of, look, you can see it's crossing in 3 places, okay? And there's going to be alpha, beta, gamma, or in any order you like. Now the second scenario is if there's 2 real roots, okay? And it's going to be this thing. So basically you're going to have x can equal alpha, like before, but this time x can equal beta, okay? And that's it. So in other words, it's still kind of crossing places. There's still really 3 roots here, of course, because this thing, this x minus beta all squared, is the same as saying x minus beta and x minus beta. And it's basically the equivalent of having equal roots. So beta is, if you like, there's your second root and there's your third root. Okay, so realistically there is 3 roots there, but we don't normally bother writing that because we just say they're an equal root in the last situation. I've drawn a little diagram here, so it's going to be one root here, and it's just going to touch, okay, where the graph turns, whereas before it turned down here or up here. Okay, so it actually passed through the x-axis. Here it just touches the x-axis, and likewise here it just touches the x-axis, and that's what happens when you get an equal root. If you're unfamiliar with any of this thing, go back to your quadratic examples and your quadratic roots, and then it should kind of start to make sense. Okay, your last scenario is your 1 real root. Okay, so you've got this thing, the x minus alpha still, so your root will be alpha, but then you'll also have a quadratic sort of multiplier, so that will be your other root. Your quadratic will be your other root. Okay, so you'll try and factorize this thing, and then you'll get your second and third root. Okay, and it's this thing, so it crosses through the x-axis, but then it doesn't actually cross through the x-axis in the over here. And likewise in the negative example, it doesn't cross through the x-axis. So we say that that's not a real root. Now remember, what I said before. There always has to be 3 roots, okay? Because it's a cubic, so the highest power is 3, so therefore there has to be 3 roots. Now, I've been looking at all the real roots. If you haven't got, like in this example, there's only 1 real root, well, where's the second and third root gone? Okay, in the 2 real roots example, the second and third real root was kind of hiding. It was an equal root. But in the 1 real root, it's fairly obvious that there isn't a second and third real root, but there has to be 3 roots. So it just means that now the second and third real root, sorry, not real root, the second and third root have to be complex. Okay, and let's look at a little bit scenario. So this is we're going to look at this thing. So in other words, this quadratic doesn't factorise, and that will give us a complex solution. Okay, so I'm going to look at, first of all, just ordinarily factorising a quadratic. So we've got this quadratic, set it equal to 0, and we'll factorise it into 2 brackets. And we're going to have roots of x equals beta and x equals gamma. Okay, and so let's just do a little bit of an example. So I'm sure you can all do this. I'm going to set up your brackets first. Okay, and remember you're looking for 2 things that multiply together to give you 2 and add together to give you 3, and they're fairly obviously going to be plus 2 and plus 1. Okay, which is going to give roots of x equals minus 2 and x equals minus 1. Okay, and those are going to be your 2 roots. So that's an example with real roots. Now remember, if it doesn't factorise into nice little brackets, then you have got a backup. Okay, and it will always work with this backup, and that is your quadratic formula. Okay, and here's your quadratic formula. Now, if it's real, then this thing, this square root here, it's called the discriminant, is going to either be equal to 0 or it's going to be greater than 0. If it's non-real, it's going to be less than 0, because effectively you're going to take a square root of a negative number, which you can't do. There's no real number which allows you to dictate the square root of a negative number. Okay, so say like if it's a square root of minus 4, okay, you can't do that because this is obviously less than 0, so it's going to be imaginary. Let's do an example with non-real roots then. So you've got this thing. Okay, x squared minus 2x plus 26, and this is your third root effectively. We're trying to try and find the second and third root. So let's use a quadratic form because I don't really like factorising this. Well, in fact, we know it is not going to factorise because I've done it earlier. But I'm going to tell you it's non-real roots, so therefore it's not going to factorise. So not even going to waste our time. So let A is hiding at the front. It's a 1 here. B is minus 2. C is 26. It's always nice just to set this up to make sure that you're definitely doing the right thing. Okay, so now let's use our quadratic formula, and here it is. It's this thing here. Okay, so x equals minus b. So be careful here, because b is minus 2, so there's already a minus out the front, so it's going to be minus 2. I'm just going to have the plus minus square root of b squared, so it's going to be minus 2, all squared, minus, I'm actually just going to move this thing down here. There we go. Minus 4 times a, which is just going to be 1, times c, which is going to be 26, okay? And that's all going to be over 2a, so 2 times 1. Okay, so let's do this a little bit of tidying up. So negative, that's going to become positive, so positive 2, plus or minus the square root of minus 2 squared, so it's going to become 4, minus 4 times 1 times 26, it's going to be minus 104. Okay, all over 2 times 1, it's just 2. A little bit of tidying up again, so this is going to be 2 plus or minus square root of 4 minus 104. Well, that's the same as doing a negative 104 plus 4, so that's going to be minus 100. All over 2. Okay, and let's break this negative root of negative 100. So we already know this is going to be using imaginary roots, but I've already told you it's going to be using imaginary roots. But we can tell because this thing's negative, so the discriminant is less than 0. Okay, so we're going to have 2 plus or minus square root. Separate the negative. This is the same as doing negative 1 times 100, just using surds here. All over 2, and let's break this square root up into 2 square roots. So 2 plus or minus the square root of negative 1 times square root of 100, all over 2. This is going to come 2 plus or minus square root of 100 is 10 times root 1. Now root negative 1, sorry. The square root of negative 1 is just an imaginary number, it's I. Okay, and that's all over 2. And now that becomes 2 over 2, which is 1, plus or minus 10 over 2, which is 5i. Okay, and so that is our third root. Okay, so we've got 2 roots. We've got x equals, from this quadratic up here, we've now got two complex roots. We've got 1 plus 5i, and we've also got 1 minus 5i. Now if you look, these two things are conjugates of each other, because remember, you can tell a conjugate because these signs in the middle are always going to be different, right? So here you got plus, here you got minus, everything else the same, they're conjugates, and they're always going to be conjugates because of this plus minus in the quadratic formula anyway. So now let's go back to our original question. Scroll all the way back up here, and I'll write it in this little space down here. Okay, I can actually probably get rid of that graph as well. Okay, get rid of that graph, give us a little bit more space. So, given that 2 and 1 minus 5i are roots of this equation, write down the third root of the equation. Well, I've just shown you that we're going to have we've got a case of one real root now, so this is our one real root, this is an imaginary, so the last root is going to be the conjugate of this. Okay, that is 1 mark. Right, so I've gone through all that explanation, hopefully you understand it a little bit. I've gone through all that explanation just to show you that whenever you have this situation where you've got a real root and a complex root, the third complex root is going to be given by the conjugate of the second one.